Hello, welcome to my YouTube video. I'm very excited but nervous about producing this, but I'm going to let you be the judge on this. So let's begin. I start off with a little question. Should teachers be allowed to think? Let's see where this comes from. I was watching a video of Grant Sanderson separately interviewing Stephen Strogatz and Diana Cohen. Each of them mentioned that there was a teacher in their lives who recognized their extraordinary skills in mathematics and made a special effort to get them recognized for them. No ordinary person would have the confidence to find an error in the work of a great mathematician. Yet ordinary mathematicians do it every day. Gödel showed that a logical system could not be complete. You and your teachers have the ability to challenge if you had the confidence to show why there is a better way to do mathematics. Another great mathematician, James Cannon, provided further inspiration when he showed how he accepted concepts with which he could not come to terms. Negative numbers are counting numbers. Sounds like a contradiction of what I've been taught and you've been taught. Let's show that the commutative property is not a fundamental to describing multiplication by showing that negative numbers are counting numbers. Let's build a foundation. Counting numbers begin with 1 and proceed by adding 1 to get the next. Now we ask a question. What direction do we count? Yes, counting forward is a method for performing addition. Can we count backwards? Yes. Count backwards is a type of counting when you start from a larger number and decrease to a smaller number. I want more clarification. Adding a negative number is mathematically equivalent to subtracting a positive number. Let's check now and see what the mathematical community has to say. A negative number isn't a counting number because counting inherently involves positive whole objects or amounts that are tangible and exist, whereas negative numbers represent absence or amounts less than 0. Well, all of the questions I just asked contradict what was just said, at least in my mind. I believe that we have found an inconsistency in the statement that states that a negative number is not a counting number. What do we mean that negative numbers represents absence or amounts less than 0? This is one application of negative numbers, but there are many others. By just looking at one example, one has restricted the use of negative numbers. What is important in a proof is to understand another person's viewpoint before you declare that your viewpoint is a better one. The cleverness in Jim's teaching, who I've referenced earlier, is that he allows another mathematician to clarify his own viewpoint. I merely did this by seeing that the definition of counting was based upon counting forwards. No, your eyes are not deceiving you. I just changed t-shirts. I still love mathematics. But let's continue. Okay, let's apply what we just learned. Unless I can find an application of a new definition of counting numbers, I've just done a mental exercise. Let's look at a counting process of multiplication. 3 times 2 is defined as 2 plus 2 plus 2 equals 6. And 3 times minus 2 is equal to minus 2 plus minus 2 plus minus 2 is equal to minus 6. Then, by the commutative property, 2 times 3 is equal to 6, and minus 2 times 3 is equal to minus 6. But I'm going to show you that I believe that the commutative property is not a fundamental property in multiplication. However, the reason why I do not believe this is because in matrix multiplication, we do not see a commutative action. Then from my perspective, minus 2 times 3 equals 3 plus 3 equals 6. This is not a correct answer. So let me redefine the process. In multiplication, when you count with a positive, you sum them and place a positive sign before the result. In multiplication, when you count with a negative number, you sum them and place a negative sign before the result. Do I understand what I just said? No, but it works. To test this out a little bit, what is -2 times -3? Well, -2 times -3 means sum up the minus threes and then put a minus sign in front of it. So we get -6 with a minus sign in front of it. It becomes 6. There's a little bit of foundation behind this. The way we define our negative numbers, when you add a negative number to its positive inverse, we get the identity element for addition. And from that, if we do subtraction or define the subtraction, -2 is equal to 0 minus 2, where we have taken and moved the 2 to the other side. Okay, so notice what we've basically done is drop the 0 to get this. Then, if we take this, 2 is equal to 0 minus -2. If we do the same process, we get -2. So there we have a positive number is equal to a subtraction of a negative number. This application interpretation was important to me because I could prove that -2 times -3 is equal to 6 without using the commutative property. Yet, like Jim, I had to depend upon something that I knew, but I did not fully understand. So let's see some consequences of this. If I have 4 to the first power, that can be written as 4 times 1/2 times 2. And I could commute those to get 4 times 2 times 1/2 before this. And then that's equal to 4 to the second power raised to the 1/2 power. So 4 squared is 16, and the square root of 16 is -4 and 4. We get an extra answer, which we wouldn't have had if we had done it in the reverse order, taken the square root and then squared. From this, we could conclude that multiplication is not computative when used in exponents, something that I observed when I was in college and asked my teacher about this, who said, nope, numbers in exponents are just like the numbers that are not in exponents. You might feel uncomfortable with this example, so let's try another. The square root of -2 minus -2 would be -2 in the way we interpret what a square root means. The square root of 2 times 2 would also be equal to 2. And so what we observe that -2 times 2 and 2 times 2 is equal to 4. I feel a little bit more comfortable with this example. So now let's get to the real part of the matter, the distributive property. Now this leads us to the following. 5 times 3 is equal to 5 times, replacing 3 with 1s, which when multiplied by 5, come out to 5 plus 5 plus 5. By the definition of multiplication, that's 3 times 5. So it looks like from this little exercise, we've shown that the commutative property is derived from the distributive property, thus no longer being a fundamental property in multiplication, which now makes me understand why multiplication of matrices is not commutative. There's a little bit more work that has to be done in order to confirm that, and that work will be related upon this particular process we did with conventional numbers. We have just shown that commutative derived multiplication can be derived from the distributive property. Now let's look at another example in here. 0. 2 times 0 is equal to 0 plus 0, which is 0. Then 0 times 2 is equal to 0 by the commutative property. Whoops, we're not finished. Hello again. No, I've changed shirts again. Maybe I'm a magician. Well, to me, sometimes mathematics does seem like magic. But let's continue our conversation. So now I'm going to redefine multiplication. Multiplication is defined as 3 times 2 is equal to 2 plus 2 plus 2. But I'm going to redefine it as 3 times 2 is equal to 0 plus 2 plus 2 plus 2. Since the result is the same with either answer. Now, I'm not so clever on this. A friend of mine has discovered this, probably along with lots of other people, that this is a better way of defining multiplication. Let's look at patterns. 3 times 2 is equal to 2 plus 2 plus 2. Dropping a 2, I get 2 times 2 is equal to 2 plus 2. Dropping another 2, I get 1 times 2 is equal to 2. But in this case, to go to the next step, I'm not dropping a plus 2, but I'm dropping a 2. And all I'm left with a blank. How do I interpret that blank? Well, some people like to interpret it as 0, but I can show other cases using exponential example that kind of conclusion will give you the wrong results. So let's now see it with the 0. I drop a plus 2, drop a plus 2, and drop a plus 2, and I'm left with a 0. By defining multiplication this way, we do not have to use the commutative property to prove that 0 times 2 equals 0. By just questioning the definition of a counting number, we have a major impact on the understanding of math. When I first presented these ideas, I was at the receiving end of much laughter. This forced me to keep redoing earlier work over and over so that I could firmly convince myself that my viewpoint was valid, despite that I didn't understand why minus 3 times 2 is equal to minus 6. The next step is to put this forth to peer review. Answer comments on the YouTube, and that'll give you an answer ability to communicate with me. So the summary basically focuses on the performance of teachers. Why does this have to do with teachers' skill in math? I have taught and worked with teachers. When I was teaching in a school in the SUNY system, I taught the students math differently from the way it was usually taught. Students who had been teaching aides told me that principals would not allow them to teach outside the curriculum. However, these same students taught their own children with my techniques. The 4 people who I mentioned as inspiration in the work had teachers who recognized their capabilities and went beyond the system to give them the opportunity to be leaders in mathematics. In one personal case, when I recognized the innate ability of one of my students at the math and physics exploration, I had to write a letter to her guidance counselor to allow her to take an advanced math course. In some of the interviews with grants, the interviewees mentioned with some reluctance of what they thought about math education. Teachers must teach a standard way. If they do not want to jeopardize their careers. There are many teachers who will slightly challenge this requirement to give more to their students. Schools have had to go through too many changes in a curriculum to go through another change. By challenging the foundations of math education, I am hoping with the help of other mathematicians to provide an as easy path for teachers to feel more comfortable about what they're teaching. Thank you very much.